Hey everyone, this is Dr. Walker. This is video 85, and in this video we're going to see the connection of simple harmonic motion, its connection to uniform circular motion. I think this is pretty fascinating. So the idea between the connection of simple harmonic motion to uniform circular motion is that uniform circular motion projected onto one dimension is simple harmonic motion. So what does that mean? Well, think about circular motion, such as here you have this ball that is moving on a turntable, and you're projecting that onto one dimension. So for example, let's say that you have a light here, and it's casting a shadow here, and you're looking at the motion of the shadow. You're projecting this motion onto one dimension. If you look at this projection, it's the same as simple harmonic motion. This applet here that shows it a little bit better. So let's push play here. What we see is this ball that is going in a circle, that is our uniform circular motion. And then we see a spring oscillating up and down here, and a spring oscillating left and right here. We also see motion being plotted. So let me go ahead and reset, and let me do it just step by step a little bit. So as the ball moves up, you can see that its position is plotted over here, and it has the same height as the vertical spring. Its position is plotted, and what kind of shape is it going to make? Well, if it has the same height as the spring, it's going to make that sinusoidal wave, right? That simple harmonic motion. And now that we've looked at this, let's go ahead and look at the x position. See how the x position also matches. So that's what we're saying. When we're looking at one dimension, it's the same as simple harmonic motion. And we can play it, but now you see it maps out that sinusoidal wave, and the motion can be represented by simple harmonic motion. You can say in two directions, depending on which direction that you're looking at. And the last thing is we can prove that the motions are the same. Let's consider a particle P that is moving in uniform circular motion. So we have a particle P right here. It's at this angle phi relative to the x-axis at time is 0. And then it moves to this angle theta at time t. And it's moving with a constant angular speed omega. So this is uniform circular motion. So at time t, the angle is omega t plus phi, right? Because it's phi plus this angle, and this angle depends on the speed and the time. Consider this the average speed times time gives you this angle. So all we have to do is look at the x component of the position. At time t, this is the x component of the position. What is this x component? Well, the hypotenuse is a, and it's cosine of theta because it's adjacent. So the x component of the position is a cosine theta. Now all you have to do is plug in what theta is equal to, and we get the familiar motion of a mass on a spring. So I just think it's really fascinating that they have the same types of motion, so I just wanted to share that with you.